shortcut to understanding the most critical advancements in AI. We cut through the noise and deliver the insights that truly matter directly to you.
Our goal is to go beyond the headlines, really dissect the core innovations and understand their potential to reshape the future of artificial intelligence.
Today, we're embarking on a deep exploration of a fascinating new technique for efficiently fine-tuning large language models, activated LoRA, or aLoRA.
Yeah, and our exploration is going to be guided mainly by the research paper Activated LoRA, Fine-Tuned LLMs for Intrinsics from IBM Research. We've also added our own analysis to, round things out.
Right, so our mission today is pretty clear. Demystify aLoRA, pinpoint exactly where its innovative power lies, and discuss why this development could be a really pivotal step forward in how we build and use AI.
And it's timely, isn't it? I mean, as we all know, large language models are increasingly becoming the workhorses of AI, powering just a huge range of applications.
Totally. But the challenge, as you know, lies in efficiently adapting these massive models for very specific kind of nuanced tasks.
Exactly. That's the bottleneck we often face.
Okay, so let's get straight to it. To really grasp the significance of aLoRA, we first need to understand its foundation, low-rank adaptation, or LoRA. Okay, let's unpack this. In essence, what makes LoRA interesting in the first place?
Well, fundamentally, LoRa gives us a parameter-efficient way to fine-tune these huge language models instead of the really computationally heavy task of retraining billions of parameters.
Which is just massive.
Right, massive. LoRa focuses on adapting only a small set of newly introduced low-rank matrices. So you can think of it as adding a very precise layer of specialization onto a general-purpose AI.
Okay, so rather than doing a complete overhaul on this giant machine, you're making really targeted tweaks to just a few key parts to get it working better for a specific job. That makes a lot of sense, intuitively. And we've seen LoRa be pretty effective, haven't we? Especially for, like, static applications.
Precisely. LoRa really shines when you adapt a model for one single well-defined task. But the research points out a pretty crucial limitation. It crops up in more dynamic situations like multi-turn
Like
interactions.
chatbot, yeah?
Exactly, chatbots or maybe intricate reasoning pipelines where the model needs to switch smoothly between different specialized skills. That's where the standard approach starts to, show its cracks.
And this is where it gets really interesting. What's the actual bottleneck? Why is it so hard to rapidly switch between different LoRa setups?
So the core of the problem is all about the key value, or KV, cache, inside the attention mechanism that drives these
The
LLMs.
heart of the transformer, basically.
Right. The model pre-calculates keys and values for all the tokens that came before in the conversation, and this KV cache is absolutely vital for speeding up the generation of the next token.
Okay, speeds things up.
But when you switch between different standard LoRa configurations, you're basically forced to recompute this entire KV cache right from the start. You have to apply the new LoRa weights across the whole history of the interaction.
Oh, wow. Okay, so every single time you want to use a different specialized skill, you're making the model reprocess the entire conversation history with the new parameters. That sounds incredibly inefficient.
It is, especially for long chats or complex workflows.
Yeah, like restarting a whole program just to use one different feature. Ouch.
That's exactly the inefficiency that activated LoRA, or aLoRA, was really engineered to solve. It brings in a fundamentally different way of thinking about adaptation, one that tackles this KV cache recalculation problem head on.
All right, lay it out for us. What's the core innovation here? What makes aLoRA different?
Okay, the central idea, the real innovation of aLoRA, is in how it selectively adapts the model's weights. Specifically, aLoRA only modifies the weights for the tokens that appear after the point where it gets activated.
After activation.
Yes. And this difference, which might seem subtle at first, it has really profound implications for efficiency.
Wait, hang on. So it leaves the weights completely alone for everything that happened before it was activated. How does that save computation?
This is the absolute key. Because aLoRA restricts its adaptations to only the tokens, it can directly leverage and, crucially, reuse the base model's KV cache for all the tokens processed before it was activated.
Ah, I see.
This allows for almost instantaneous switching between different specialized aLoRA bodies without that huge overhead of recomputing the entire cache.
That's a game changer, instant switching. That opens up so many possibilities. The paper talks about intrinsics in this context.
Yeah.
What exactly do they mean by intrinsics?
Yeah, intrinsics. You can think of them as these highly specialized, very lightweight models. They're meticulously designed for very specific, well-defined jobs within a bigger conversation or processing sequence.
Okay.
And aLoRA makes building and using these intrinsics much more practical because you can call them up on demand with minimal computational costs, all thanks to that KV cache reuse.
Right.
It's sort of like having a whole suite of finely tuned instruments in an orchestra, each one ready to play its specific part instantly when needed.
So instead of one giant model trying to do everything, you have a core base model handling the main flow, and then you can just activate these specialized intrinsics for very precise tasks when you need them. It feels much more modular.
Exactly. Modular is a great way to put it. The authors also connect this to the idea of late prompting. Can you maybe elaborate on why that's a relevant comparison here?
Sure. As I understand it, late prompting is basically when you give the model the specific instruction after it's already processed the initial content.
Mm-hmm.
This lets the model's initial understanding of the content be more general, right? And potentially reusable for different tasks, depending on what prompt comes later.
Precisely. And aLoRA cleverly uses this same principle for efficiency. The base model processes the input first, building up its KV cache that's like its general understanding of the context.
Okay.
Then when you call up an aLoRA intrinsic, it's like giving a late instruction. It guides what happens next, guides the generation, but it still gets to benefit from all that initial heavy lifting already captured in the base model's KV cache.
Okay, the core concept is definitely clicking into place. Let's dig a bit deeper into the technical side now. How does aLoRA actually achieve this selective adaptation? Architecturally speaking, the paper mentions the attention mechanism.
Right, so just quick refresher, the attention mechanism computes query, key K, and value V matrices from the input tokens. Standard LoRA, as we said, adds low-rank adaptations by tweaking the weight matrices that produce Q, K, and V. Those are WQ, WK to BV. It adds these small LTQ, the LAK, eta V matrices.
Right, across all the relevant tokens. That's how it adds just a few trainable parameters to guide the fine-tuning.
Exactly. Now, equation 4 in the paper is really key here. It mathematically spells out how aLoRA applies this adaptation. For tokens they call X, after the ones that come after the LoRA model is activated, the adaptation matrices LAQ, LK, LTV are applied.
Okay.
And this is crucial for X before, the tokens before activation, the original unmodified base model weights, WQ, WK, WV, are kept.
Ah, so the elegance is in that conditional application. It only applies the adaptation after a certain point, and because the base weights are used for X before, the KV cache built using those weights is still totally valid and reusable.
That's it. That's the heart of the efficiency gain right there.
Makes sense. The paper also talks about an invocation token sequence. What's that about? What does it do, technically?
So this sequence basically acts as the trigger. It's the signal to the system saying, okay, activate this specific aLoRA model now. It marks the exact point where the weight adaptation switches from the base model to the specialized aLoRA parameters.
Just an on switch, then?
Well, yes, but the authors point out it can be more than just a simple switch. It actually offers some neat architectural advantages.
Like what?
For instance, it makes it easier to integrate LoRa into existing chat templates, right? So it plays nice with established ways of interacting. Plus, you could design the sequence to include a short task-specific prompt or some initial context just for that aLoRA model.
Oh, interesting. So you could give the specialist a little heads up.
Exactly. Potentially refining its performance right from the start by giving it more focused input.
That sounds pretty flexible. Efficient switching, easier integration, maybe even better performance. Now, one thing the paper notes is that aLoRA often needs a higher rank R compared to standard LoRA to get similar performance. Why is that?
Yeah, that's an interesting point. It comes down to how standard LoRA can subtly influence the KV cache over the entire sequence.
How so?
Because standard LoRA adapts weights for all active tokens, it can kind of indirectly tweak the keys and values of the past context. It can embed information there that helps with generating future tokens. It shapes the whole contextual representation.
Okay, so it can sort of bake in forward-looking hints into the context itself.
You could say that, yeah. Now, aLoRA can't do that for the tokens before it's activated. It has to work with the base model's KVs for that initial part unmodified.
Right, because it only kicks in later.
Exactly. So to make up for not being able to influence the past context directly, it often needs a higher rank, particularly in the query adaptation, the SIQ part.
Okay.
This higher rank basically lets the aLoRA model ask more sophisticated questions, query more effectively of the base model's existing KVs to pull out the specific information it needs for its specialized job.
So it needs a more powerful magnifying glass, perhaps, to examine the existing information since it couldn't shape that information beforehand.
That's a good analogy. It needs more refined probes, yeah.
But, crucially, even with this potentially higher rank, it's still way, way smaller than fine-tuning the whole model, right?
Oh, absolutely. The researchers make that very clear. Even with a higher rank, these aLoRA adapters are still substantially smaller than the base LOM. The core benefit of parameter efficiency is definitely preserved.
Great. Okay, let's pivot to the practical side. The paper shows off several really compelling use cases for these aLoRA and intrinsics. Let's start with uncertainty quantification. What's the innovation there?
Right, uncertainty quantification. The innovation here is creating an intrinsic that can give you a probability estimate of how confident the base model is in its own answer.
Wow, okay. Self-awareness for the LLMs.
Sort of. It outputs a score, like 0 to 9, which maps on in a calibrated confidence range, say 5% to 95%. It lets the AI system actually express its own level of uncertainty about what it just said.
That seems incredibly useful for reliability and transparency. You don't just get an answer, you get a sense of how much to trust it. How do they train an aLoRA to do that?
It's quite a clever process, actually. It involves two stages. First, they train a separate little probe model. Its only job is to predict whether the base model's answers are correct on a diverse data set.
Okay, a correctness predictor.
Yep. And then they carefully calibrate this probe so its predictions translate into reliable probabilities. Then they use this calibrated probe to create a teacher data set, basically labeling the base model's outputs with these predicted confidence scores.
Ah, so the probe teaches the aLoRA.
Exactly. The aLoRA model is then trained on this teacher data set. It learns to predict these confidence scores when it sees a special certainty token or sequence.
Makes sense. And how would it perform? Did using aLoRA hurt the accuracy compared to standard LoRA for this?
That's the impressive part. The performance was remarkably similar. The mean absolute error, or MAE, for aLoRA was 0.49, and for standard LoRA it was 0.50, almost identical.
Wow.
Yeah, it really shows that aLoRA can deliver this crucial uncertainty info without any significant accuracy drop compared to the more computationally hungry standard LoRA method.
That's a really strong result. You get efficient self-assessment without needing big, slow external judge models. Okay, what was the next intrinsic showcasing aLoRA's potential?
The second one they looked at was answerability determination. This is super relevant for retrieval augmented generation RAG systems.
Ah, yes, right. Where the model looks up information in documents before answering.
Exactly. The innovation here is an intrinsic specifically designed to figure out if a user's question can actually be answered based on the documents the system retrieved. Is a straightforward yes/no classification. Is it answerable from this context or not?
That could massively improve RAG systems, right? Stop the model from just making stuff up when the info isn't there.
Precisely. Stops hallucination based on retrieved context, or lack thereof. They tested this aLoRA on both single-turn and multi-turn QA benchmarks.
And the results.
Again, really positive. aLoRA's performance was right there with standard LoRa, and in some cases, even slightly better at correctly identifying answerable versus unanswerable questions.
So again, efficiency without losing the ability to make these critical judgments in information retrieval. Very cool.
It holds up really well.
Okay, two very persuasive applications. What other specialized skills did they test out with aLoRA?
The third intrinsic was query rewrite. This one is particularly innovative, I think, for improving multi-turn conversations with AI.
Right, because as the chat goes on, my questions often depend heavily on what we just talked about, which can mess up things like retrieval later on.
Exactly. Pronouns, implied context, it gets messy for downstream tasks. So the query rewrite intrinsic tackles this. It takes the user's latest query and basically decontextualizes it.
Meaning?
It turns it into a standalone, self-contained query that something like a retrieval system can understand properly. It resolves pronouns, fills in missing bits from the context, makes it independent of the chat history.
Okay, so it takes my vague, context-heavy question, like, what about that one, and turns it into, what is the efficiency of the aLoRA query rewrite intrinsic?
Precisely that kind of transformation. And they evaluated how well this worked by looking at the quality of retrieved documents using recall.k and also the quality of the final answers generated using metrics like RAGA's faithfulness and RADbench.
And how did the aLoRA version stack up?
Guessed it, the results showed the aLoRA query rewrite performed very, very closely to the standard LoRA version. Once again, the efficiency boost from aLoRA didn't really cost anything in terms of the quality of the rewritten query or the final answer.
Okay, the theme is definitely holding. aLoRA equals efficiency without a performance hit across these different specialized tasks. What was the last intrinsic they looked at?
The final one we'll touch on is jailbreak detection. Obviously a super important area for AI safety and responsible deployment.
Absolutely. We need good ways to stop users from tricking models into saying harmful things.
So this intrinsic is trained specifically to spot user prompts that look like they might be jailbreaks attempts to bypass the model's safety filters. It's another binary classification. Jailbreak risk present, yes or no.
And the performance, let me guess.
Yes, consistent with the others, the aLoRA model achieved comparable performance to standard LoRA on accuracy, true positive rate, and false positive rate for detecting these risky prompts.
So aLoRA can even help make LLMs safer, again, without the computational cost of traditional fine-tuning. That's a really compelling set of examples showing the innovation. Let's shift gears slightly now to the inference efficiency advantages the paper highlights. Can you spell those out?
Certainly. Figure 4 in the paper gives a really good picture of this. They use an example of an agent pattern. Imagine a base model generates an answer,
Okay.
and then you want several specialized evaluators to check different things about that answer. Maybe one checks facts, another checks sentiment, another checks if it followed instructions.
Right, like a panel of specialist reviewers, each looking at one aspect.
Exactly. Now, if you built those evaluators using standard LoRAs, each one would force that recalculation of the KV cache for the entire conversation history plus the generated answer.
Ugh,
Yeah. So as you add more evaluators, the computational cost and the memory needed just explodes. It becomes prohibitive really fast.
I could see how that would scale very poorly.
But with aLoRA, it's different because each aLoRA evaluator only adapts weights for its own little evaluation task, and the base context is already processed.
They could all reuse the base model's KV cache.
Exactly. All the aLoRA evaluators can share and reuse that same base KV cache. This leads to massive savings in both computation time and memory usage.
Makes perfect sense.
And figure 5 in the paper shows this visually. As they add more aLoRA evaluators, the performance impact is minimal. But with standard LoRAs, the performance tanks significantly as you add evaluators. That scalability is a huge practical win for building complex AI systems.
That's a crystal clear demonstration of how aLoRA's core innovation translates directly into real-world efficiency gains. Okay, so let's try to summarize. What would you say is the absolute central architectural innovation that aLoRA introduces?
I'd say the core innovation is its ability to enable really efficient dynamic adaptation of LLMs for these specialized tasks, the intrinsics. And it does this through that fundamental mechanism of reusing the key value cache for the context before activation.
And the direct results, the key benefits stemming from that innovation.
Primarily, you get significant speedups during inference and much lower computational costs. This is especially true in dynamic situations like multitask settings or long conversations. And critically, you get this efficiency boost without really sacrificing accuracy compared to standard LoRA.
It really does sound like aLoRA brings a new kind of modularity, a new level of efficiency to how we can build and use specialized AI skills.
Exactly. By making it easy and cheap to switch between these specialized intrinsics, aLoRA really opens the door for developing more adaptable, more responsive, and ultimately just more sophisticated AI applications.
The paper also mentioned some ongoing work and future directions. What's next for aLoRA? What are they exploring?
Well, they're actively looking at using aLoRA in more complex agentic systems, systems that need to string together sequences of different specialized tasks. They're also looking into test time scaling, and importantly, they're working on integrating aLoRA with VLLM.
Oh, VLM, the optimized inference engine.
That's the one. That integration sounds really promising because it could make aLoRA even faster and more practical for developers to actually use.
Yeah, that sounds like it would really boost its real-world impact and make it easier for people to adopt.
Absolutely, it's a key step.
So as we wrap up this deep dive on Activated LoRA, let's leave you, our listener, with a final thought. Really consider the implications here. What does it mean to have the power to instantly switch between highly specialized AI capabilities? How could that fundamentally change how we interact with AI, how we build AI applications? What brand new possibilities does this unlock, perhaps in your own field? Maybe for creating incredibly personalized experiences, or for tackling complex problems in ways we haven't even thought of yet. This feels like a genuinely innovative step with the potential to really reshape the AI landscape. Thank you for joining us on the Deep Dive.